So first we're going to talk about polymorphism, and then we'll break and make a separate video because people don't like to watch videos that are an hour long. Right? So 15 minutes maybe. We'll see. So I want to focus on what happened at the end of Lab 3. And this is the step 6, I think, from Lab 3. So you had to go back to the shape class and add public methods called getPerimeter and getArea that returned 0, which is obviously stupid, but they are methods of the shape class. And you remember that shape has descendants, rectangles and circles. But we didn't actually talk about creating any shape objects per se. But if we wanted to send a message to a shape object, at least that message would be syntactically correct. You could say to a shape object of any kind, whether it's actually a shape or whether it's a rectangle or a circle or anything else that descends from shape, you could send a getPerimeter message and something would happen. It would not fail because of a syntax error. So then what we did was we created an array of shapes, and let me show you what that looks like because that's right here. And if you look right there, we have this array of 10 shape objects. But we didn't instantiate any shapes, even though that's perfectly legal in terms of the way we set up the shape class. We could have created a shape object, but we didn't. We created rectangle objects, we created circle objects, and then we stuffed them into various locations in the shape array. So this array of shapes actually holds rectangles and circles, not a single shape object. But remember, I'm lying right now because everything that's a rectangle is also a shape. Everything that's a circle is a shape because those descend from shape. And so you actually have two types. We talked about this the other day. Okay, so in the shape class, we had this array. I'm sorry, in the main, we created an array of shape objects, and then we sent the getPerimeter message and getArea message to each of those elements. And the powerful thing that's happening there, in case you didn't notice it, down here, we are sending this getPerimeter message to an object, and we don't know what kind of object that is exactly, except that it's a shape. And so what is happening is determined right then and there. It's not determined earlier at the time this program is compiled. It's determined when the actual object is in there. And this is important, and it's at the heart of what's called polymorphism. And that's where I want to start today because you all had that experience with polymorphism. So this is what we did. We had an array of shape objects. We put rectangles and circles in there, and then we sent getPerimeter and getArea messages to those objects, and all we knew about them was that they were shapes. And we can't know at compile time what it is exactly that we're talking about. This is important. At compile time, you can't know this, particularly because what got put into the array could have been the result of a user saying, I want this kind of object, or I want that kind of object. Imagine an if statement in the middle of a user interface that asks the user, what kind of shape do you want? And the user says, I want a circle. And then if the user says circle, you instantiate a circle object and throw it into the shape array. Okay, so at compile time, you can't know because the user is making those decisions. So this is kind of important, and it actually has a name. All right, so back up a minute. Polymorphism is one of the 3 pillars of object-oriented programming. Those 3 pillars are encapsulation, inheritance, and polymorphism. We've talked about inheritance, and I've mentioned encapsulation from time to time. It's an elementary thing, but it comes back over and over again. The idea of information hiding, the idea of chunking information so that it's protected from outside influence and only changed by things that should be able to change it. And there's more to it than that, and we'll come back and mention what that is as we move along. But polymorphism now is this new idea that we want to focus on for the first part of today. So polymorphism is the ability to associate many different meanings to one method name. So you have one method name, like getPerimeter, but what will actually happen depends on what kind of object you're talking to. And you might not, and you probably cannot know what kind of object you are talking to until execution time. So the way that this works is something that any computer science person needs to know, and we call this late binding, sometimes called dynamic binding. So in inheritance, which is one of the mechanisms that supports polymorphism, we'll be talking about another mechanism in just a couple of days, but inheritance allows a base class to be defined and other classes derived from it, and then you can have objects of the base class if you want, or you can have derived class objects. But the beauty of this is that you can also send these messages to any of the derived class objects, and the messages will be interpreted by the derived class objects in their own way. So if you're talking to a rectangle and you send this get perimeter message, the rectangle responds in its own way. The circle responds in its own way. So all of these methods have different ways of operating, and we never say, if you are a circle, do this. If you are a rectangle, do that. Every object simply responds in its own way. And that's what polymorphism is all about. Late binding technically means that what a method will do, the definition of a particular method, is not determined until execution time, until the time when that message is sent to that particular object. And at that moment, we know what the method is supposed to do. As opposed to early binding, where we would make that determination at compile time. So when a program is compiled, you should know what all the methods are, what they mean. Well, that's not what happens with polymorphism. With polymorphism, you cannot know at compile time. So at execution time, when the message is sent to the particular object, then the method definition is bound at that point, and that's when we determine what exactly happens. So not binding the method early at compile time, but binding the method at execution time, late in other words. So that's what late binding is about. If the method definition is associated with its invocation, when the method is invoked at runtime, that's called late binding or dynamic binding. Java uses late binding for everything except private, final, and static methods. And so you can write a method in a base class to perform a task even if portions of that task aren't yet defined. That's exactly what we did with getPerimeter and getArea. We defined those methods at the base class in a dumb way, just return 0, expecting that our children will override those methods, and then it's the method that is being invoked for that particular object that is the one that's actually bound at runtime. And so that's what we did here with shapes. And at that point, we will pause. That's it for introduction.